Okay, this is just me running through the topic test that you completed for chemistry, just going through the answers and how you would make sure all your answers are correct. You can use this marking your own topic test, or you can just watch this video as a study for your half yearly or yearly coming up. Okay, so first we have here calcium carbonate was added to a solution of hydrochloric acid. The flask contents and balloon were weighed before and after the reaction. The products of the reaction are water, carbon dioxide gas, and a solution of calcium chloride. And it says here, which is really important, it says construct a word equation. Now, it's really important that we understand that we want a word equation. Remember, calcium carbonate and water are words, and CaCO3 and H2O are chemical equations, which we'll do in the next question. But to focus on the question at hand, what we have here is we've got to construct a word equation. I'm just going to zoom in a little bit so I can neatly write this here. So first thing we have is calcium carbonate. So cal carbonate plus hydrochloric acid. And that goes to water plus carbon dioxide and then the last thing we have is calcium chloride. Okay, so just zoom out. Let's make sure we have that all there. So for this first question, word equation, calcium carbonate plus hydrochloric acid goes to water, carbon dioxide, and calcium chloride. Okay, so for this next question here, it says construct a formula equation. So now we're using the chemical symbols for the things used for this reaction. So it says show a line of working. So for showing a line of working, the first thing I would do is just a basic unbalanced line of the equation in chemical notation. So CaCO3, fix that A up, plus HCl, and this will go to H2O plus CO2 plus CaCl. Okay, so looking at that and comparing it with the one above, calcium carbonate and calcium carbonate, hydrochloric acid and hydrochloric acid, water and water, carbon dioxide, and calcium chloride. You will notice the differences is we've now expressed that in that chemical formula equation that we've been asked for. Remember, the first thing to do for an equation like this is always look at if you have any ionic salts produced. So remember, a salt is a metal and a non-metal. So a perfect non-metal we can find is right here. And so you look for those in the products. And if you see them in the products, the first thing you're going to do is use those little numbers, those subscripts, to make sure that salt is balanced with its charges. Okay, so when we make sure that we have that balanced salt with its charges, we should know that calcium is 2+ and chlorine is -1. So you can go the swap and drop method, where you would swap the 1 over to this side and drop it down, and you would swap the 2 over to this side and drop it down. Or you can go the method of just thinking about it in terms of numbers, where we say if we have a +2 and we have -1 and we want to get to 0, then we need 2 of the -1s to cancel out the +2. Either way that you use, you should be able to get to saying that calcium chloride is going to have a small 2 here. Okay, so that can be your first line. Now that you've got that first line done and you have the salt balanced, the second line should be the actual balanced equation itself. So this is where you use those large numbers, or sometimes we said they were called coefficients. Okay, so replicate that same equation. So CaCO3 plus HCl goes to H2O plus CO2 plus CaCl2. Okay, and now we can get to balancing. Now, the first thing to do when we're balancing, or the easiest thing to do, I think would be making sure that we balance the calciums first, because they are the metal, and you really want to make sure that we balance the metal first. So there's one calcium on this side and one calcium on the other. That's fine, so we can move on. Next, we can see we have one carbon on the product side and one carbon on the reactant side as well, so that's okay. We will get now to chlorine, and we'll find that we have two chlorines here on the product side, and we have one chlorine on the reactant side. So what we're going to have to do is use our big 2 in front of this HCl to give us those 2 even chlorines. And when we continue on from there, we will also see that there is the H2. There's 2 hydrogens in the water on the product side. But given that we've already put that 2 in front of HCl, we actually have 2 hydrogen on the reactant side as well. So this equation is balanced. The very, very last thing we can do to get our full marks and get a perfect equation is make sure we put some states. So remembering that calcium carbonate would be a solid, hydrochloric acid would be aqueous, water is a liquid, carbon dioxide is a gas, and calcium chloride is aqueous as well, okay? Because we know that it's aqueous because it is a solution, which we can see here. So we can actually be able to ascertain that, okay? So moving on, next question. Use any of the terms in the list below to identify each of the reactions shown. So sodium carbonate plus hydrochloric acid, carbonate plus acid. Now that should be your first indication that this is an acid-carbonate reaction. But the second thing we should notice is that our products are salt, water, and carbon dioxide. And when I say salt, remember a salt is any ionic bond. So any metal and non-metal that's bonded ionically is going to be our salt. So here we know that this is a acid plus carbonate reaction. Next up, we have magnesium hydroxide plus sulfuric acid goes to magnesium sulfate and water. So magnesium sulfate is a salt, and we have water. You should also notice here that magnesium hydroxide, Mg bracket OH bracket 2, our magnesium hydroxide there is going to be a base because we have hydroxide involved. And sulfuric acid, obviously by the name, tells you that it's going to be an acid. An acid and a base is going to always be neutralization. Okay, so there's neutralization. Calcium carbonate going to calcium oxide and carbon dioxide. Now, this is a pretty classic example of a decomposition reaction. Okay, decomposition reaction, we learned about those. Also, just thinking about it logically as the root of what decomposition is, we can see that we have one reactant breaking apart or separating through the reaction into 2 products, as if it's decomposing or breaking down, okay? The last thing that we have here is butane plus oxygen goes to water and carbon dioxide. This is combustion. Okay, when we have combustion, it's always things like hydrocarbons, which is things like this. Now the X and the Y here can represent any number, or we also saw throughout our topic that sometimes we have that OH on the end, which makes it an alcohol. Either way, those 2 things mixed with oxygen always gives us a combustion reaction. So there's those answers to those 4 there. Moving down, so the table below shows the symbol or formula for several ions. Now, it's good that you're given these ions and the name of these ions. That should really help you throughout this question. And it actually will help you answer some other questions throughout the test. If you forget what a carbonate is in other questions, it's actually written here for you. So you could refer back to that. So in an exam, just make sure if you get a table like this that you are looking back on it and making sure that you have it with you. So write the chemical formula for magnesium nitride. So here we see that magnesium is 2+, referenced in the table, and nitride is N3-. Okay, now we can do our swap and drop here by putting the 3 over here and bringing it down, and bringing the 2 over here and bringing it down. Now remember, when you drop, you also drop the charge, okay? And that number actually stops denoting charge when you swap and drop, and now denotes how many of each atom you have. And when I say denotes, it just mean it tells you. Okay, so Mg3, N2. And that makes sense because if we have 2 nitrides, that's 6-. And if we have 3 magnesiums, well, each is 2+, so that gives us 6+, 6+, 6-. We've got ourselves a neutral salt. Again, looking back up here, we have aluminium, which is denoted as 3+. And we have hydroxide, which is OH-1. Now, the tricky thing here, and this is a really important thing, whenever you have an anion, and by anion, I mean a charged ion that's negative, so a negatively charged ion is an anion, with more than one type of atom, so it's polyatomic, and polyatomic means there's just more than one atom that makes up this anion. You need to put brackets around when you are having more than one of them in your salt, just because the bracket actually multiplies the whole ion because it's made out of more than one. And I'll show what I mean. So aluminium is 3+. If we do a swap and drop, we'll see that the 1 will go over here and drop down. Now we don't write the 1, and with the 3 will go over here and drop down as well. And so when we actually do that, what we would get is we would see that we basically need 1 aluminium and we would need 3 hydroxides. So we need 3 hydroxides, but a hydroxide is made up of 2 or more atoms. So what that means is we have to say bracket OH, bracket 3. And now what I'm saying is this 3 multiplies everything in this bracket by 3. So we have 3 OHs like so. If we just wrote OH3, that would mean we just have 1 oxygen and 3 hydrogens, which isn't what we want. We really need to put that bracket, and you would not get marks if you wrote OH3, because that is not the right ion. That's not what we're looking at. Okay, so that's what your right answer would be. Make sure you're looking for those brackets whenever you have an anion or a cation. The only cation you guys are mainly going to see that has more than one is NH4. Okay, that's the only sort of cation that we're going to see made up of more than one type of atom for year 10. However, just be really aware that if it's made up of more than one type of atom, you're going to need to use those brackets if you need more than one of them. That's a really important point. So calcium sulfate, as we scroll up, calcium is Ca2+, Ca2+, and sulfate is SO4 2-. Okay, which is all good. 2 plus 2 minus, this is actually CaSO4. Some of you might do a swap and drop and try and think that it's Ca2SO4 or bracket SO4 bracket 2. Because they're the same charge, the simplest way that they would go together is just a 1-to-1 ratio because they already naturally cancel out. Just be aware of that if you're going to try and do swap and drop. Just check first that they're not already the same value of positive and negative and would already just cancel out. That's another important mistake that people can make. So naming chemicals, or naming salts, I should say, this is something that can be mixed up. So all we need to remember is that if the anion is polyatomic, or just more than one atom, we do not add the "-ide" ending. So do not add the "-ide" in that case. However, if we see that the anion is monoatomic, okay, that's very messy, sorry, is mono or one atom, we do add the "-ide" ending. So we do add "-ide." Okay, so it's just, that's the main sort of naming convention. And then on top of that, cation, the cation always first. So cation always first, okay, which means anion after. So that's a really important point that I think we need to be aware of. So what we have here is AlSO4. Now, Al is aluminium and SO4 is sulfate. Now, SO4 is our anion, which we just did in the above question here. So that's SO4, that 2- there. We should be able to say that this is going to be aluminium sulfate. Okay, so if we go up, we should be able to see both of these if you're confused on the spelling or anything like that. So A-L-U-M. I'm going to have to double check how to spell it myself. I-N-I-U-M. Sulfate. So aluminium sulfate. We spell it with a F in Australia. Sulfate. My mistake. Aluminium sulfate. Okay, and because the anion is that 2-, the anion is made up of two different types of atom. This is sulfur. Here we have oxygen. We know that we do not need to add the "-ide" for that very reason. Next up, we have magnesium. And then CO3 is carbonate. Okay, now again, CO3 is the 2-, it's the anion. The anion is the negatively charged ion. Carbon and oxygen, which means it's two types of atoms that make up the negative part or the anion. We don't add the "-ide, so this is just magnesium carbonate. Calcium hydroxide we have for the next one here. So here we have calcium, here we have hydroxide. So calcium is this one here, hydroxide is this one here. Okay, and the same as before, so calcium hydroxide. Okay, again, OH, we making up the anion, so we have an O, we have an H, so two different types of atoms. We do not add the "-ide." This type of question actually, unfortunately, doesn't give you the other end where the anion is. We do add the "-ide. So just for reference, let's say we had CaCl2 or calcium chloride. Notice how I say chloride, and that's because that Cl is -1, so that is one type of atom. Now, it's really important that we understand one type of atom. Even though it's Cl2 and there's two of them, it's two of the same type of atom. Those two Cls are the exact same thing, so it's still one type of atom making up the anion. So we do add the "-ide there. That's where that "-ide would come into play, and it's calcium chloride, not calcium chlorine. Okay, so another example of that could be calcium oxide, for example. Now, oxygen's 2-, calcium's 2+, so the simplest ratio is just 1 and 1. So notice how, again, calcium oxide. I added the "-ide. That's because the only thing making up the negative charge is that one 2-, that one oxygen there. So it's not about how many of the ion there is, it's about how many different atoms are within that anion, which is a really important point. And there is stuff on the OneNote about doing this again if you really want to practice, or you can come see myself or any other teacher should be able to help you out. Okay, complete the following table. The first one has been done for you. So this is a question asking you to understand basically coefficient and subscript. So coefficient, don't know what happened there. So coefficient and subscript. Okay, we really got to try and understand both. I'm not sure why that won't circle, but hopefully we can understand the point that I'm trying to make. So, okay, really just doesn't want to do that. So anyway, what we can look at here is we see that we have number of different elements. Now, different elements is the same as different atoms and number of atoms in the whole compound. So here we have zinc and we have carbonate. Okay, so we have zinc carbonate essentially. Really doesn't like to be highlighted, but we're just going to work with it. So because we have zinc carbonate, we have one zinc, we have one carbon, and we have 3 oxygens. Now, zinc is a type of element, carbon's a type of element, and oxygen is a type of element. So there's 3 different elements. It doesn't matter that there's 3 oxygens. It itself is just one different element that's in this compound. And now thinking though, we have 1 zinc, 1 carbon, 3 oxygen. The total number of atoms is going to be 5. Okay, so we have 5 for that compound. So let's do the next one together. So we have 2BaCl2. I think the easiest thing to do at the start is just work out how much of each. So looking at the first one, the number of elements. Ba or barium is an element and chlorine is also an element. So we would have 2 different types of elements that are in this compound. And I think the easiest way to figure out the total number of atoms is just figure out how many is in one total and then multiply. So here we can see we have Ba, we have 1 of those, and we have 2 chlorines. So 1 Ba and 2 Cl. That basically means that we have 3 atoms per molecule or per compound of this. And there is a giant coefficient 2 in front. So 2 times 3 is 6. So we have 6 total atoms in this compound. Next one, this one's a little bit tricky. So it's just a little bit long-winded, which is fine. Sorry, I'll just make sure I re-add those. So we had 3 in here. Sorry, we had 2 in here. So 2 in here, and then we had 6 in here. Okay. Next up, we have Na2SO4. Okay, so just looking at the first one, sodium's a type of atom, sulfur's a type of atom, and oxygen is a type of atom as well. So looking here, it looks like we have 3 different types of atoms in here. So 3 different types of atoms. Next up, we can see that we have a big 3 out the front. And that's going to really multiply a lot of these numbers. So for one molecule, let's just have a look. We have 2 sodiums, we have 1 sulfur, and we have 4 O's, or 4 oxygens. Okay, so 4 oxygens, 1 sulfur, because there's nothing there, so you assume there's a 1, and there is a 2 there. So what do we have here? We have 1, 2, 3, 4, 5, 6, 7 atoms per molecule, and we got to multiply that by 3. Now 7, 14, 21, we should see that we have 21 atoms in this total number that we're given here. So 21. Okay, and that's just using those little numbers and then multiplying it all by that coefficient there. Okay, classify the following compounds as ionic or as covalent. So for this one here, remember a metal plus non-metal is going to be ionic, and non-metal plus non-metal is covalent. Okay, now that we know that, we can work through. Now, you would be provided a periodic table in your exam, but I don't have one, or I can't quickly jump to one. So I'm just going to make reference. So potassium chloride. Potassium is a metal. Chloride is not. So we've got KCl. Barium is a metal. Hydroxide is not. So again, methane, carbon is not a metal. Hydrogen is not a metal. So that would be covalent. Aluminium oxide. Aluminium is a metal. Oxygen isn't. So Al2O3. Carbon dioxide is carbon is not a metal. Oxygen is not a metal. Okay, and water H2O, hydrogen is not a metal. Hydrogen is not a metal, and oxygen is not a metal either. So that's what we're looking at there. Using terms like gained, lost, and shared, compare the electrons in ionic compounds with electrons in covalent compounds. So covalent compounds is sharing electrons. Okay, covalent is sharing electrons. Ionic is loss and gain of electrons. Now, you might want to make this more of a nice sentence or a pretty little paragraph in your exam, and that's fine. You could say things like, in covalent bonding, the electrons are being shared between atoms, and then you could say in ionic bonding, there is a loss and gain of electrons between atoms, okay? And that would get you full marks, but as long as you sort of raise these important points and do what the question asks, make sure you talk about a gain and loss and shared. So there you go. There's the three words that we really got to use. Okay, so write a balanced chemical equation for the corrosion of aluminium plus oxygen. Okay, so this can definitely get a couple of people because a lot of people approach it in different ways. One thing I would really recommend in this case, if you look at the test, it actually gives you a lot of the answers. So aluminium plus oxygen, we can actually see here that aluminium oxide, it tells you what aluminium oxide would look like in this above question. So if you just read that, you could even start with that Al2O3, just so you know what you're dealing with. And it also says up here that aluminium typically has a charge of +3. Okay, so it does actually tell you a lot of the information that you might like to use, which is really important. So Al, okay, we know we have our aluminium there and plus oxygen. So typically we say that if you have oxygen, just assume it's O2 because it's reacting with oxygen in the air, which exists as O2. And then you might say that it's aluminium oxide. So again, I did say in the above question, it does actually give you the answer is Al2O3. You might want to write AlO, that's fine. And remembering that oxygen is 2- and aluminium is 3+, you can do your swap and drop, and you'll actually get to the same thing. So you'll be able to get to Al2O3, okay? Which, look, I know sometimes under stressful tests, test conditions, you can miss things, but just remember to read questions and use information that you have, all right? Use what you have always. I think that's pretty important. So doing some balancing here, because it does say a balanced chemical equation, which is important. It's really important to make sure we can do what we need. So just making reference to things, this one can be a little bit tricky. So one thing that we can do is if we put a 2 out here, okay, that 2, because we're working with tricky numbers, because we have O2 and O3, that can be a little bit hard to deal with. So what we're going to do is if we put a 2 out here, now we have 4 aluminium and 6 oxygen, which means we could put a 4 here like that, which would be fine. And we could put a, we could put a 3 here. And that is balanced, okay, because 4 aluminium is on this side, there's 4 aluminium here, there's 2 times 3 oxygen, which is 6, and there's 3 times 2 here, which is 6. That's fine. You can definitely do that. Some of you will go down the route of what we've seen in combustion. So you might say, well, there needs to be 2 aluminium here, and then you might say, well, you need to have 3 on 2 oxygen here, okay? Or you need to have 1.5 times 2, which is 3. Both of those are fine. At your year 10 level, you would get marks for either of those, okay? So both of those are fine. If you did the fraction version or if you just use the whole numbers, that's fine. Remember, if I times all of this by 2, I would get exactly what I had a second ago. And I would have the 4, 3, and 2 here. And that's if I times that fraction. So look, while this isn't the most simplest representation of the equation, it's still one that you would get marks for at our stage. Oh, and let's not forget, we would probably have some solid aluminium oxide, some solid aluminium, and some gas oxygen, okay? Write a word equation for the combustion of octane, which is a major component in petrol. So word equation and its combustion. Again, reading the questions that we have, we actually set up here what combustion was. This told us, okay? So we know the products that we're going to get are water and carbon dioxide, and we're reacting with oxygen, which is actually a really important point. Again, I just want to reiterate using the test to your advantage. Okay, so octane plus oxygen, and we can say gas, we know it's oxygen, gas, goes to, oh, I'm just going to probably run out of room, so I'm just going to go again, sorry. So octane plus oxygen goes to water plus carbon dioxide. Okay, there we go. Word equation. We use some words. We didn't use chemicals. Now we say write a balanced equation for the combustion of methane, CH4. So it gives you what methane is. You don't have to know that, which is a major component of natural gas. Cool. So here we use the actual chemical equation. So same thing as above, except now we're using chemical. So same equation, but in chemical notation. So CH4 plus O2 goes to H2O plus CO2. Cool. Balancing, so new line, I would, as I said, write a basic equation first, and then let's balance it and add some states and make sure everything's looking good. So CH4, let's do carbons. There's 1 carbon here, there's 1 carbon here, that's fine. Hydrogens, we have 4 hydrogens here and 2 hydrogens here. Now that is obviously no good. So we would need to, as we rewrite this, and write it in a way to balance, we would definitely need to put a 2 here, because now we multiply that 2 by this 2 to give us the 4 hydrogen that we want. Last comes oxygen. Remember, when you're balancing the equation, always leave hydrogen and oxygen till last in that order. Do oxygen last. It just will make things a lot easier usually. So we have 2 times 1 here, and then we have, so 2 times 1 oxygen, sorry, so in the water, so 2 times the 1, and then here we have 2 oxygen, so we have 4 total. Here we have O2, so we just got to chuck a 4 there, okay? And then we can make sure that we know this is gas, water is a liquid, and carbon dioxide is a gas as well, okay? Really important. This question formulated very strangely, but basically it is making a graph on the iodine clock. Now, it can be really hard to draw a graph on this, so I'm just going to attach, you should look in the file that you find this video. You'll find that this graph, there is an exemplar of this graph with the marking scheme that we have of a graph attached. So just make sure you look at that file again. It can just be a little bit messy to do with a texter like this. And I want to give you an accurate sort of depiction of what that looks like. So just hold off on that for now, and we'll go through the rest of the tests. So the trend in the graph, we should see, well, we can kind of just identify it here. As we increase the volume of hydrogen peroxide, it shortens the rate of reaction. So 30 mil takes 8.5 seconds, where 7.5 mil takes 29 seconds. So that's kind of a trend. And again, just look for the separate file about that part. So explain the effect of concentration. This part we can do here and now. So remember, increased concentration. Well, that's not very nice. So increased concentration causes more molecules are available for collisions, which increases the rate of reaction. Okay, so if I have more molecules in a solution, there's more molecules moving around, and just statistically, if more molecules are moving around, you're going to get those molecules colliding with each other more. Now remember, a chemical reaction is a fruitful collision. It's molecules colliding with each other with enough energy to break bonds and in the correct orientation of the actual molecules or atoms or compounds that the reaction can occur. So a fruitful collision with enough energy, correct orientation, causes the reaction to proceed. And if you have more atoms moving around or an increased concentration, you naturally are going to get more collisions and increased reaction rate. So that's how you would answer that question there. Okay, so a student investigated putting nails in different solutions or liquids or combinations of liquids, oils, vinegars, waters, Coca-Cola, etc. And here's some photographs from that experiment. Very cool. So are these results qualitative or quantitative? Now, this isn't a chemistry question. This is just a science question themselves. So they used their senses. So they use their senses to get these results. There's no numerical data attached to this. So these are qualitative. Okay, suggest a chemical name for the dust observed. Now, I know a lot of people might kick themselves for not getting this one. Rust is fine. And if you're really feeling fancy, you could definitely say iron oxide. But rust will do you just fine, okay? That is technically a chemical name. A word equation for this. So you could have iron plus oxygen going to iron oxide. Pretty simple word equation that will get you across the line if you wanted to do something like that. I know we traditionally say to write O2, thinking about it as oxygen in the air. So this would go to FeO. Because there's 2 oxygen here, there needs a 2 to be here, and there needs a 2 to be here. So either way that you wrote it, you would get marks for it at the year 10 level. I know a lot of you just naturally write that 2 there because you assume it's oxygen gas in the air. That's fine. And you would get marks for that. So here's another version of that. Oh, I'm sorry, I made a mistake. It actually says a word equation, and I wrote a chemical equation. So I'm making the same mistake of not looking at the question. All right, word equation. So iron, geez, that's having a rough try. Iron plus oxygen goes to iron oxide. Okay, so that's all you need to do there, word equation. So as I do, not as I say. Write a chemical equation for copper corroding in the presence of O2. Now we can do our chemical equation, all right? So Cu plus O2 goes to CuO. Okay, now this is going to be an ionic bond because we have a metal and a non-metal. So because we have a metal and a non-metal on our hands, we've got to do charges. Now, copper, remember what I said, if you have a metal that's in the middle of the periodic table or a transition metal, just assume that it's going to be 2+, unless you're told with Roman numerals it's not. So sometimes you might get things like Fe, sometimes you might get things like Fe like that, okay? Don't, obviously if you get that, assume Fe 3+, because it tells you with the Roman numerals. But if you just have Fe like we have here, assume it's 2+, okay? Same goes with copper. So if we have copper that's 2+, O2 is covalently bonded, we don't worry about that, but we do know that oxygen by itself is 2- and 2+. So the good thing about this is we have 2+, 2-, we don't need to balance that salt. Next thing we do is balance the whole equation. 2 oxygen here, which means we've got to put a 2 here, which means we've got to put a 2 here. Okay, so that's fine. You would get 1 mark for writing it generally, and you'd get another mark for balancing it. You could also split what I just did across 2 lines as well. That's fine. Independent variable of this experiment is the solution. Male was in, okay, because that's what they changed. And the dependent variable was the amount of rust on male. Okay, because that's just, remember, the dependent variable is what you change. Sorry, the independent variable is what you change, and the dependent variable is the thing that changes because you change the independent variable, or it's what you're measuring. Okay, last one. Red cabbage can be used to make an indicator to test the acidity of substances. A student did this for a variety of household things, vinegar, soda water, shampoo, dishwashing liquid, etc. And we got them in that indicator. Okay, so it's really hard to see, but you can see kind of lime, vinegar, soda, shampoo, dish soap, tap water, milk going down there. So in there, it asks you to look at that and try and classify things based on what we say. And here, the question tells you, here's your 2s, 3s, 4s, 5s, 6s. So correlating that to a color. And that's the pH scale right there, which we've learned about and should know of. Okay, so just working through, starting with lime juice. We can see it kind of there. Lime juice is, lime juice is looking at around the 2 mark, so a pH of 2. A low pH is an acid. Sorry, the milk is first. It's not in order, my mistake. So milk is this one here. So that's a very sort of light bluish color. This one here, I would say 8. You might get the marks for 9, depending on who's marking and who's feeling nice. But I would probably put that in the 8 category. So pH of 8, that is basic. Anything above 7 is basic, anything below 7 is acidic, and anything that is 7 is neutral. Now we have our lime juice, which is 2, which is an acid. Now we have Napisan. Now let's have a look at Napisan. Now Napisan's all the way over here and is 11, okay, which is super basic, okay. pH scale goes up to about 14, so Napisan is actually pretty basic. Baking soda, okay, let's have a look if we can find some baking soda, and here it is right here, and that's looking like a pretty solid 9/8. I'd probably accept both. I'm just going to put 9. Definitely basic though. Tap water looks like a very solid purple, which is 7. Here's tap water here. Okay, so that's 7, which is neutral. Last thing, we have vinegar, which is this one right here, that sort of pink solution. And here we see that as well. So I'd put vinegar as a 3, which is acid. Okay, I really should say acidic, to be honest. Okay, for all of them, instead of writing acid, but it's a bit here nor there. So look, that's the whole topic test. As I said, look for a file attached on the graph section. It's just a little bit messy to do through here. Any questions or anything I've went through in here that was a little bit confusing, please just let me know. I'm always happy to help you. Any of your teachers are. But these are the solutions. Hopefully I didn't make any mistakes throughout them. And so look, if you're watching this, I hope it's helped with revision. I'm sure not all of you will watch this. But for the ones who do, I really hope it helps you out in your studies. Any questions, please come see me. Thank you.